Let's solve a few problems on gravitation. Problem 35 from page 235 asks, what is the acceleration due to gravity on the surface of the moon? What is the acceleration due to gravity on the surface of the moon? So we recall that acceleration of gravity is in general gm over r squared, in which m is the mass of the planet, moon, etc., and r is the distance from the center. If we are at the surface, if the question is about acceleration of gravity at the surface, then of course little r becomes big R, which is the radius of the respective object. So in this problem we want to find the acceleration at the surface of the moon. So we go with 6.6 times 10 to the negative 11. That is the gravitational constant. Then we need the mass of the moon and the radius of the moon. So if we go to table 2 in our book, we are not given the mass of the moon in the table, in table number 2. We have to look up the mass of the moon, no problem. So the mass of the moon, as long as the object is specified, we can look it up. So the mass of the moon is 7.347 times 10 to the 22 kilograms. And the radius of the moon is another quantity that we can find, radius of the moon. It is 1,737.1 kilometers. So we have to multiply by 10 to the third, and we have to square this. So if we plug in all the numbers, we get an acceleration of 1.62 meters per second squared. So we notice that acceleration at the surface of the moon is about 6 times the acceleration at the surface of the Earth. Oh, 1/6. 1/6 acceleration of the Earth, right? The acceleration of the Earth on the surface of the Earth is obviously 9.8 meters per second squared. Another typical question in this chapter has to do with satellites. So a good question would be problem 47. Problem 47 on page 236 that says that astronomical data indicates that Milky Way has a mass of about 8 times 10 to the 11th masses of the Sun. So this is the mass of Milky Way. It's about 8 times 10 to the 11th times greater than the mass of the Sun. And a star is orbiting the galaxy at about 6.10 to the 4th, the radius, let's call it little r. We should reserve little big r for radii of planets. So at a distance of 6 times 10 to the 4th light years. And they're asking us, what is the period of this star? What is the period of this star? Well, so we have Milky Way of mass m, and we have another star here of mass little m. Right? So we know that this star orbits Milky Way, the center of the galaxy, with a radius r 6 times 10 to the 4th light years. And we are asked to find the period of this star. Well, we know that the centripetal force is equal to the force gravitational attraction between the two. So the centripetal force mv squared over r is equal to gmm over r squared. Little m goes away. Notice that in the problem the mass of the star is not given. 1r also goes away, so we are left with v squared is equal to gm over r. On the other hand, we know that the period is 2 pi r over v. So if we bring this expression here, so this will become 2 pi r over square root of gm over r, or 2 pi over square root of gm r square root of r. And this is nothing else than Kepler's third law, which we derived in a separate video. So now it is just a matter of plugging in the numbers. But of course, we might not be that comfortable with the units of light years. So let's convert. Let's see what 1 light year is equal to. Well, 1 light year, as the textbook mentions, it is the distance traveled by light in 1 year. So 1 light year is a distance. So we have to use the speed of light multiplied by time, and the speed of light is 3 times 10 to the 8 meters per second, and the time is going to be 1 year. But of course we want to convert years to seconds, so 1 year will be 365 days, or 365 times 24 hours, or 365 times 24 times 60 minutes, or 365 times 24 times 60 times 60 seconds. So if we put all these numbers in a calculator, 365 times 24 times 60 times 60, we end up with 1 year being 3153600 seconds. Of course, we can also Google this if we want, right? So let's keep this number in mind. So the radius in this problem, 6 times 10 to the 4 light years, so it would be 6 times 10 to the 4 light years, which would be 6 times 10 to the 4 times 3 times 10 to the 8 times 3153600. This will be in meters. So obviously it is a huge number, as we can expect. Times 3 times 10 to the 8 times 6 times 10 to the 4th. So I get 5.68 times 10 to the 20 meters. So now if we come back here, the period will be square root of 4 pi squared, radius cubed, so 5.68 times 10 to the 20th power 3, divided by 6.67, 10 to the negative 11 is G, and the mass 8 times 10 to the 11, multiply the mass by the mass of the sun, which is given in our book. It is well, it is given in the book somewhere. We can find it. So the mass of the sun is 1.989 times 10 to the 30th. Huge numbers, as you can imagine. So this will be in seconds. So if we plug in all these numbers, let's see what we get. 4 times pi squared times this one cubed divided by this times 8 times 10 to the 11th times 1.989 times 10 to the 30th. I get something, and then I need square root of that. I get a period of 8.25 times 10 to the 5th seconds times 10 to the 15th seconds. And if I convert this to years, I will simply divide that by that huge number, and I end up with 2.62 times 10 to the 8th years. So a huge period. So notice that we used Kepler's law, Kepler's third law, but we have this new unit, the light year, which is by definition the distance traveled by light in 1 year. So we're simply doing distance multiplied by time.